So let's look. Now, all this was a kind of intro. So let's look very concretely now at how you can use the neural network framework to solve this problem. And the reason we, now we move to the framework is that when we don't want to scale up using the symbolic word of formulas, we want to scale up using the neural network framework. So here I'm defining what is called linear layer. Linear layer is like a generalized version of what I did so far that can, take matrix multiplication between arbitrary tensors. So, vectors, matrices, 3D tensors, 4D, any D. Maybe not, there's a limit, probably upper limit, but very high. I want right now to mimic the problem we had before, so I'm just saying input real, output real. Yeah, and this is telling me this. And you see, inside the framework always uses arrays of tensors. So the fact that it's a real number is basically just stripping. It's a vector of length 1, and it's stripping the vector out at the end. So you see this the weight is my alpha, and the biases is my beta. So this now is a 1-by-1 matrix and a length 1 vector. But this, you can see how we can scale up. Okay, so you see some red here. This red means that it's the equivalent of being symbolic. Like, this is a program that has not been initialized with the random values for alpha and beta. So I can use a function net initialize to I should look at my keyboard here to put in random values. So now this is ready to be used, and actually, spoiler, let's use it now. If I put a number, I get a number out. Yeah, so cool. And if I want to look at what's inside, I can use functions to access this object. So for example, here I want to extract, and you see here, you always have these elements that you can highlight and you can click on them. So like if I click on this and I paste here, I see weights and biases. So this stuff here, you can always, what you have here, you can click on and you can always put in net extract to figure out later. So here I want to extract weight and biases, and you see that this is a real 32 numeric array, because in Mathematica arrays are typically real 64. And we don't want that much precision. It's yet another place where you want to cut corners. So modern transformer, they are heavily quantized. They do stuff in 8 bits, 4 bits, 2 bits. It's kind of funny that we went from float to double, and now we are going back down to very, very small ways of encoding numbers. But yeah, but by default we use 32-bit reals, and you can use normal to see what they are. So you see that alpha and beta here are like 0.6 something and 0. But by default, the constant part that you add is initialized to 0, and the multiplication part is randomly initialized. So you see that now, like applying the network to a number, and actually this is why I had these numbers evaluated. Let's do this and let's do this. Okay, and this is our operation directly. They are exactly the same. Yeah, of course you don't want to do this. You want to stay with the network. Okay, so now let's recast these data in a format that can be used to do some actual training. And in Mathematica, you use this arrow syntax. So this input goes to output. Now here I'm applying the network as a function. Neural networks in Mathematica, they work like they are normal object. They work as a function. You can just put that data in. So here I put my this one here. This blue one is my data, and this relationship here is my model, which is completely random again, and these are my errors. So I start with the line, so the errors are aligned. That's quite easy. Now, how do I do the gradient descent procedure? You don't have to do anything manually here. You just put basically two things: the network and the data into a function called netTrain that is performing the training. So basically, this is the minimum thing that you need to do. Yeah. Just to make sure that we are reproducing exactly what we did before, I'm being extremely verbose here. So I'm putting the network, the data. I'm explicitly saying that the loss function is mean squared loss, which is, again, another type of layer. This is a layer that takes two input, my input and my target, and gives me the loss out. You see, this one here is doing, it doesn't know, it says array here because it can be anything. But here it says real because it's always an average. So it, even if this is uninitialized because it doesn't know it has no parameters, strictly speaking, but it has also no shapes. But it knows always that the output is real, so it can say that. And this is something that we do in general in the framework. If we know what port is called, what stuff comes in and goes out is, we tell you. Otherwise, we stay generic. Okay, say let's use method stochastic gradient descent. Let's start with this learning rate. And here I put some function to do some reporting. So you can see that, this is my loss function that is going down. And here is, okay, now it's already minimized. This started here, now is like this. Let's start again. Abort and start again. Yeah, okay, this is too fast. I should slow it down a bit. But you see, I mean, this already, it learned the slope immediately, and then it took a little more to learn the what is called the bias, the beta term. But this is a very simple problem, so it had basically no problem figuring it out. Okay, so now at the end, if I plot this, I see my prediction. Of course, it has some noise. My training data, my prediction stays on this line, and it's a pretty good prediction. So I mean, this is solving the same problem that we had before, but in a much more general way. So now what we can do is we can complicate things and throw stuff at the framework.